Yes. All right. Yeah. So welcome for another CSP seminar today. So I wanted to, Leigh will introduce the speaker, but I just wanted to thank the sponsors of the research areas, NCIS and SP, for this seminar series. We have a whole semester full of it, so if you like what you listen to, please come by. Yeah. Go ahead, Leigh. Always.
Okay. So today we have a great pleasure to have Chijing. Chijing is an assistant professor at electrical and computer engineering at Princeton University. He got his PhD in computer science at UC Berkeley with Michael Jordan, and got his bachelor's degree in physics from Peking University. His research interest lies in theoretical machine learning with special emphasis on non-convex optimization and reinforcement learning. I think today he's going to talk about reinforcement learning. And his representative work, including proving noisy gradient descent, accelerated gradient descent escape saddle points efficiently, proving sample complexity bounds for optimistic Q-learning, which I'm very familiar with. My student and myself have been looking at his paper very carefully. And least square value iteration and design near optimal algorithm for min-max optimization. So today he's going to talk about a provable multi-agent RL in large scale space. I think it's related to the min-max optimization, if I understand correctly. Yeah. Okay, so Chi, please go ahead. Yeah.
Thanks, Leigh, for inviting me, and thanks for the introduction. Today I'm going to talk about our recent work in reinforcement learning theory, and it's going to be a compile of two works. And basically, we all know reinforcement learning, and today I'm going to talk about the reinforcement theory, and we focus on two parts. One is how we deal with a large state space, that is function approximation, if you know the terminology. And the second part is how we deal with multiple agents. This is a joint work with Qinghua Liu and Sobhan and Tianchen Yu. I'm Chijing from from Princeton University. First slide is my wonderful collaborators. Both Qinghua and Sobhan are my students currently at Princeton University, and Tianchen is our long-term collaborator who is currently a PhD student at MIT. An overview of results, I guess most of you I think every one of us are facing sequential decision makings every day, like from this robot task or autonomous drive or poker or even Go. Basically, sequential decision making problem is any problem that we need to make a sequence decision. So we need to first make a decision and see what is the feedback from the environment. And then based on that feedback, we make the second decision. So once we have this make a sequence decision and based on the feedback from the environment, this is like sequential decision making. And the main framework in machine learning is to use the reinforcement learning framework to address those kind of tasks. So typically when we talk about reinforcement learning, we're under the model so-called Markov decision process. Basically, the reinforcement learning tasks is we have both agents and we have an environment. And we can take this robotics robot. He is trying to fold tau as an example. So the environment is going to feed states. So in this case, it's kind of like the position of tau and also the angle of the joint of the robot. And the robot is then going to take action. And that is like, for example, apply some torque on the joint of the robot. So the action is going to change the environment, and the environment is going to move to the next stage. So we have the next position of the tau and next angle of the arm. And eventually, environment is also going to feed the reward to the agents. And that is like if we successfully fold the tau, we get a reward 1, otherwise we get a reward 0. So reinforcement learning is about this feedback model. And the goal of reinforcement learning is we want to find the best policy to maximize the cumulative rewards. That is, in this case, we want to find the best way to fold the tau for the robot in the long run to maximize the success rate, for example. And the most important thing here is we assume the environment is usually fixed. So we have a fixed dynamics. So the physics law will not change in this scenario. And in terms of reinforcement theory, we typically care about efficiency, which is most important criterion we look at in theory. So in terms of efficiency, there are two types of efficiency. One is so-called sampling efficiency. The other one is computational efficiency. What do we mean? Like sample efficiency is basically how many samples or how many games, how many passes we need to run to learn the optimal policy. And computation is, by its names, is like how long we need the computer to run. It's a week or a month. Just let's have an idea of what is the state of art models do. Like for example, the AlphaGo 0 is a model implemented by Google DeepMind to train on the problem of Go. And the good model, it was trained on more than a million, actually 10 million games. And it took a month of a whole computer cluster to train those models. So basically, even the current successful model is trained with a tremendous amount of samples and like a huge amount of time. And definitely to go further on the road, like to develop reinforcement learning, we do want to decrease the sample complexity. We also want to decrease the computation efficiency. That's why, like in theory, we care about both of them, and they are kind of also very helpful for practical purpose. So it turns out there are also a lot of classical theory on the reinforcement learning. Some of the very old reinforcement learning theories are not about sample efficiency and computation efficiency. They are about designing some algorithms so that they are correct if samples and the computation like runtime goes to infinity. Recent reinforcement learning theories, however, look at sample complexity and computational complexity. And typically, we actually already have a lot of very good results focused on a setting that is a single agent and a tabular setting. So single agent means I only deal with one agent, and tabular is like I have a small amount of states. However, what happens in practice, as my name suggested, is like we want to deal with both multi-agents and the large state space. So we will see what are those challenges. The first challenge is instead of tabular setting, we do want to look at the large state space. What do we mean here? Is the classical IL, we call it classical reinforcement, we call it tabular setting. That is what it means is the number of states and actions are both finite and small. For example, if you look at the chess game, even the chess game number of states is already not that small, but at least it's finite and it's reasonable, like millions or 10 millions. So the strategy for those tabular cases for the standard reinforcement theory is we just visit all the reachable states and learn from them directly. So we know this state is reachable. In this chess game, the states means like the position of each pieces. And if I can somehow reach these states, and I will just play until I reach these states and learn from there. So as we said, there are already a lot of results about this setting. And one is we can do like some VI with upper confidence bound. And our previous paper, as Lei already introduced, we're doing some Q-learning or optimistic Q-learning in that kind of regime. However, what happens in practice is not about this tabular setting. It's actually so-called function approximation setting. So what does it mean is like in practical problem, like for example, in this StarCraft, each state is kind of corresponding to the value of like all the pixels. So in this case, we have tons of pixels, typically like already like 1 million pixels, and each pixels can taking like, for example, like at least like 20 or 50 like different values. So number of states is actually huge. It's typically like at least greater than 10 to the 100. And we clearly know if we want to enumerate or just goes over all the states, that's not possible. And especially like when we learn how to play StarCraft or how to like do the modern reinforcement learning applications, most states are not visited even once. So we clearly need a new mechanism to learn those kind of reinforcement learning tasks. And the current strategy to do that is so-called function approximation. By its names is that we will approximate the value and the policy, which we'll introduce later, by functions or parameter by functions in a parameter class F. So we will not study like arbitrary values of functions, but we will given like a parameter class, for example, like deep neural networks, which is like what typically do in current modern reinforcement learning systems. And we will use this deep neural nets to approximate either value or functions. So in this way, we learn the reinforcement learning. And there are a couple of challenges of function approximation in theory. First, in theory, we need to say something like, by doing this, we're able to do the generalization. That is because most states are not visited even once. So we only visited a very small amount of states. We want to say the knowledge is learned so that our model is able to generalize knowledge from visited states to unobserved ones. And on the other hand, we also need to deal with limited expressiveness, because function approximation kind of like says I'm giving a parameterized function. If a function is not very rich, for example, if it's only linear functions, then a lot of functions is not inside my function class. In the algorithm, I'm going to handle the scenarios if after some computation, my function ends up outside this function class, then I need to say something about how to go back and how to quantify the errors. Finally, we also need to deal with exploration versus exploitation trade-off, which is like something we have to deal with for bandit and reinforcement learning tasks. So as a result, a lot of existing theories only focus on the special cases under strong assumptions. Special cases, what I mean is like, for example, we only deal with linear function approximation. That is, we only study the subclass that value function is only linear function. And LQR is also something linear. And very little result is about like a generic function class, like how we deal with nonlinear, deal with kernel, deal with some other stuff. Okay. This is the first part about large state space. The second part is about multi-agency. So we already know if we formulate the problem as a Markov decision process, which is standard model for reinforcement learning, we require the environment dynamics is fixed. So that is whatever the action I choose, the transition from the current state to next state is going to be the fixed dynamics. However, in the multi-agent system, this is not the case. We should not think opponent as a fixed. Opponent is clearly not necessarily just play the same strategy. He can adapt his strategy according to the strategy I played. For example, I play strategy 1 and strategy 2 in the second round, and he can see, oh, I always play this kind of strategy, so he can adapt his strategy. So the environment becomes non-fixed. And we need some new mechanism able to deal with that. And in this talk, we will consider a special case that is two-player zero-sum games later part. And to make things further complicated, we are also consider a scenario we want to do a self-play. So there are two types of learning. One is about learning with expert. The other one is self-play. Learning with expert, that means like in the multi-agent setting, only one agent is like learner. The other agents are all experts. So we can hire some experts to play games with the AI agents. We clearly know from this approach, first, it's very expensive to hire those experts. And also expert play games at different time scale with like AI. So like, for example, the experts probably for play a game, he needed several hours. However, for computer to play a game, he only needs several minutes. So this will also make the training a lot slower. We will also consider the setting that is so-called self-play, that the agent just figure out how to play the game itself. Okay. So this kind of gives the central question of this talk. Can we design a so-called sample efficient multi-agent reinforcement learning algorithm for general function approximation? I just want to clarify a little bit. In the beginning, I said efficiency, we have both sample efficiency and computational efficiency. And given the current scenario that for general function approximation, there isn't too much result exists. So we kind of like, we want to go to the first step. We first want to understand how to achieve the sample efficiency. And later we will deal with computational efficiency, which is not about this talk.
So can I ask a quick question?
Yes, go ahead.
So for sample efficiency here, are you assuming, for example, the computation capabilities like is infinite, like you can do
infinite,
yeah, okay. And
yeah, we'll probably need to solve some program that in worst cases like require exponential time.
Okay, and you can every time you can utilize all the samples you collected before the current time.
Right.
Okay, cool.
It's kind of like a statistical learning theory, which you assume you have access to ERM, which in practice you cannot compute in polynomial.
Okay, thank you.
Yeah. Okay. Yeah. I think by this sense, I would feel this is like a first step towards. Yeah. Go ahead.
So, Chijin, again, in terms of your general function approximation, are you going to assume that, I mean, your value functions will lie in that class, or are you going to
Yeah, we'll talk
because
about
there will be
later. We will assume the realizability assumption. Yes.
okay, because otherwise there is an error with the projection, anyways, right? Your function class cannot reach
Yes.
it,
And we also need something stronger than that to deal with the projection.
Yeah. Thank you.
Very good questions. So yeah, so overall, this talk we will center around two themes. One is about how to deal with multi-agency. Second part is about general function approximation. And our theoretical guarantee we're going to prove is how much samples, polynomial samples, we're going to need for those kind of settings. And the talk will have two parts. The first part will deal with general function approximation alone. So we will have some new results, which is able to define a general function class and in a single agent setting. And we say we have an algorithm that is able to solve that kind of function class. And the second step, we're going to extend that result from single agent setting to the multi-agent setting. Okay, this is overview. So if no further questions, we'll first directly step to the single agent scenario. So for the single agent reinforcement learning, we're going to study the classical model, so-called episodic MDP, and which I guess most of you, this is like the first thing you probably know if you learned reinforcement learning. And the episodic MDP, and the MDP is we already kind of like introduced. So we have states, action, and a transition probability. That is this P probability condition on current state action, and denoted if I'm currently at state 1 and take some action, and what is the transition probability to transition to the next states. And we also have a reward, that is if I'm current at state 1 and have some taking action, what is the immediate reward I'm going to get. By episodic setting, we always means the entire game or one episode is going to end in H steps, and then we stop and we start again. And the access protocol, we kind of consider the exploration setting, which is like stereo setting. So we're given initial states. For example, when we play game, we are given initial states, which is the beginning of the game. We assume it's like fixed, and then the agent is only able to take actions, and no matter what states you're going to end, it always ends up from the transition. So it's kind of like you play the game, you're only able to input actions, and you're going to end up whatever the game leads you to. And that finishes the game. We're not considered some stronger model like which has simulator where you can teleport to any states. In this case, we're just the standard weakest model that is exploring setting. We only have fixed states and we're only able to change the actions. And there are several concepts that are important to talk about, which is like frequently referred by the remaining of the talk. And the first one is what do we mean by policy? Policy means at the current states, like for example, a configuration of the chess, what is action, like what move I'm going to take. So it's a map from the current states to the action. And the other one is so-called value function. Value function is the expected cumulative reward starting from the current state action configuration. For example, in a chess game, I'm at the current board configuration, each piece at each position. I would assign a value to this configuration, says I expect starting from there, if I play some policy, like how much chance I'm going to win. So value is kind of like roughly something about this.
Sure. Just a quick clarification. So when you talk about policy mapping from state, the state includes a step as well, right? Including the HL.
Yes.
So,
yes.
Okay.
Yeah. Here is a little bit vague. So it's a state step. State also step and time step to the action.
Okay. Thanks.
In episodic setting, yeah, each step can be different, have different parts.
Right.
And the value function is also same. It also depends on the steps. So the value function at the second last step is different from value function at the very beginning.
So yeah, I had a question on that. I mean, I was basically looking at your last statement saying that you're finding pi star that maximizes V1 pi, but because your transition kernels change, actually, even if the transition kernel was the same, because your finite horizon problem, your optimal policy is time index dependent, right?
It's time different. Yeah, when I wrote this pi star means it means like pi 1 to pi h. So I have h
okay.
different.
All right. So that was the clarification I was asking for.
Yeah.
Thank you.
That's very good. Okay. Yeah, and the objective of reinforcement is just we want to find the optimal policy, pi star, so that I maximize this value. This value is like because I assume the initial state is fixed, so I only care about the value in the very like if for the starting state of the game. and I want to have a policy that maximizes this value. Okay. And this is all about classical MDP. And when we talk about function approximation, we do mean in actual to this MDP protocol, we can access to MDP. I'm also given a function class that, as I said, because the value function is different at each steps. So if for each different steps, I have a value function class that F1, F2 until Fh. And I denote this F as a Cartesian product of all the value functions. Okay. And I will also use F, this value function, without any index to denote it as a vector of this value functions. So the whole point of value function approximation, as I said, is I want to find a function inside this function class so that I can approximate the optimal value function, which is a Q star, and that is the value function denoted by optimal policy. As Vijay already asked, and typically in this literature, we do make at least one assumption, that is a realizability. I think all of the existing result kind of relies on this assumption. That is, we do assume the optimal value function actually lies in this function class, or some of the result tolerated some very small errors, but essentially it's a kind of realizable result. And the second one is some algorithm will be required, and the algorithm we're going to introduce today is we're going to require this assumption, but we also can remove it by slightly changing the algorithm, which we will not introduce today. So just keep in mind, completeness is also some assumption which is also frequently assumed. It says, I haven't introduced a Bellman operator, but I will introduce later. So it says that when Bellman operator operates on the function class of the next step, it's going to land in the function class in the previous step. This is very helpful in saying something about when you do the projection. It won't be very far, because in practice I cannot do this Bellman operator. This assume I know the probability distribution. In practice, I can only do a sampled version of this, so I still incur some error. But at least with this completeness, I'm going to say it's not going to be very far from the FH. Okay. And then in a function approximation setting, my objective change a little bit because I cannot just find an arbitrary policy which kind of like will scale with S. Even representing that policy will scale as S. So we will find a limited policy within a policy class with limited capacity. In this case, I'm going to exclusively look at some so-called greedy policy. That is, each policy is going to represent it by a value function in this function class. And how to take action by looking at this function is basically I have the value function, which is a parameter of both S and A. If I'm currently at this state, I'm just look at I'm assuming action is finite, and I just look at all the values for this current state. For example, if I have A values, and then I just look at the maximum one and then take that action. So it's a greedy action. So that means for each value function, I can corresponding to a greedy policy. And my objective is I want to find a value function inside this function class. It's not necessarily the Q star because I always have some statistical error, but at least I want to say the value compared to the optimal value is at most epsilon suboptimal. The value of induced policy minus V star is at most epsilon suboptimal. Okay, so far so good.
Yes.
Just a quick clarification. So when you say this is setting is large state space, but small, not too large an action space in some ways, because you said you were doing this conceptually doing this greedy.
Or you can also say some large action space if you can do the max over A efficiently.
Okay.
Yeah. So when we say actually I should not say like finite action because the sample complexity eventually somehow does not depend on like number of action. It only depends on some later like complexity.
I mean, wouldn't
only about in the computation like how you do the max over A.
But that seems a little. I mean, that seems a little surprising because wouldn't if I arbitrarily reduce the actions that I allow in each state, I may not get a policy. I may get a policy which is much further out, right? In some sense, the action compression should have a cost. So,
action compression should have a cost.
Yeah, because if I can look at action compression as if I have 1,000 actions, I'm only allowed to take 10 of them, unless magically the optimal action is in that 10. I'm going to pay a price. I'm going to pay a price somewhere. So how is?
Yeah, I think
I'm just trying to understand how would that not come in the sample complexity. I'm just trying to understand that.
We do assume the realizability. Is that a question?
Okay, maybe that's what takes it away. Right. Thank you.
Okay. Good. Okay, so the main question about the general function approximation, as we said, is clearly if we don't make any, so we already make two assumptions, realizability and completeness, and turn out these are not sufficient. So we do want to further structures about it. And all the existing results require a lot stronger assumptions about it. And also without any function, without any structure on function class, we can easily construct some counterexample where no algorithm would work. Just because this is like greedy, this is like a value function class, and the policy value of policy may not have any relation with a greedy policy, with the value class. So basically, the question we should ask here is, what is the minimal structure assumptions I should impose on this general function approximation? Like, I just want to have a richest like a function class of problem, so that I can guarantee I can learn them sample efficiently. Okay. This is like the ultimate question, and clearly, like it's very hard to say in theory like what is a minimal structure. But what we can do is we can do two steps. The first one is I want to identify a very rich class, and ideally they will include a lot of the class, a lot of reinforcement problems that already encountered in practice, or like we have already known how to do it in theory. And the second step is I want to design a sample efficient algorithm that learns in polynomial samples, and so that this algorithm can learn any problem in this very rich class I defined. Okay, I'm going to talk about two parts. One is about function class, the class of reinforcement problem. The second one is about sample efficient algorithms. So we can first look at the previous attempts. There are several known classes of reinforcement problem that we already know they can be learned efficiently. One work is by like a school of Microsoft research, and they kind of like says they define a so-called low Bellman rank notion, and they include a lot of classical problem like LQR, linear MDPs, tabular MDPs. They also have some fancy like examples like reactive PSRs, reactive pool MDP, basically a very special class of partial observable MDPs. The other class is a so-called low Eluder dimension. They do have some common examples like LQR and linear MDPs, but they also include some other class like a general linear MDP that is not in the low Bellman rank, and low Bellman rank also have some class like this problem is not in the low Eluder dimension. So those are like the two generic class we have known so far that essentially kind of like general and able to deal with some function approximation. And furthermore, if we talk about their algorithm to solve those problems, their algorithm kind of like specific and a little bit complicated. So, and they are also like the second one is very specific, and the first one is depends on some hypothesis elimination, like mechanism. Both of them are very different from what practitioners use, which is just optimization or just some like minimize the Bellman rank or like this neural networks type of thing. So, what is our results? First, in terms of complexity, we discover a new complexity measure, so-called low Bellman-Eluder dimension. Okay, essentially by the name, we say we kind of like include both low Bellman rank and low Eluder dimension class. So we're kind of like with a super class, and we can deal with some actual examples or actual applications, which has not been covered by previous class. And the second thing, we will also introduce a GARF algorithm. Although the name is GARF, but it's a very simple and a very generic algorithm that is able to efficiently learn any reinforcement problem with low Bellman-Eluder dimension. So this algorithm is just can deal with any problem in this function class. And to introduce this class is a little bit more technical. I probably won't have time to do it in this talk, but I would like to introduce this very simple algorithms. And you can see it's actually very simple and just stem from the very basic principle about the minimize the Bellman rank, about minimize the Bellman arrow. Good.
Yes.
Okay. Yes. Oh, okay. Okay.
Yes.
So to introduce our algorithm, we first started with a textbook algorithm, so-called fitted Q iteration. What does a fitted Q iteration means? first, I have introduced like for the MDPs, we know for all MDPs, we have the optimal policy always exists. And furthermore, the optimal policy satisfies so-called Bellman optimality equation. That is, a value function at current h steps is equal to the reward and the expectation of the next states and the max over action for the next for the Q value at the next step. And this S prime is taking over the transition probability, and A prime is max over actions. This is standard Bellman optimality equations. I can just wrote this R plus expectation and the max as a Bellman operator. So it's a Bellman operator operates on the value function of the next step. And we have a simple, and this is like to do Bellman optimality equation, we kind of we assume we need to know the transition, and we also need to deal with all the state action. But in practice, clearly we don't know the transition. We only have the sample version of that. So like a surrogate of this is we just directly minimize the empirical Bellman arrow, which is exactly what so-called fiduciary derivation is doing. So what they said is we kind of doing a dynamic programming base. We start from the very last step where the value at the h+1 step is always just 0. Then what we do is we minimize the Bellman error for each step. So the Q value I'm gonna pick for the h step is going to be the argmin of a value function in the function class. Sorry, I should have a subscript h here. So that I'm taking expectation over the data and I look at the Bellman arrow. That is my value function I'm gonna pick and minus the empirical Bellman operator. That is basically this Bellman operator, but replace this expectation by the sample version, by the sample average of the next value.
So to some extent, it's like a model-based algorithm here, right? Because you are storing all the data you have so far, and but instead of say I explicitly have model, I just say I take whatever I have the data and try to solve the problem. Yes. But it's very close to a model-based algorithm, if my understanding is correct.
Yes, to some extent, yes. And I think typically when people talk about model-based algorithm in a tabular setting, they are saying like I use samples to fill a transition probability, like a construct transition model. But I just want to say, in a function approximation setting, we won't be able to construct a transition model accurately just because the state is so large and there's no way to estimate the entire transition probability. But what we can do is instead we're looking at some expectation of the value function, and the expectation is computed in a way, as you said, like average over the data. We can store over all the data.
Right, because on the other hand, since you are storing all the data, so we don't have to explicitly estimate the model transition because whatever you can extract is already in the data. And since you are not through with the data, all the knowledge are stored, right? And the model-free case, I think in the classical definition is you just estimate the Q function and you don't actually reuse those data, I guess, right? So
I think by model-free, I think what you mean is more like online style of algorithm, like Q-learning, which is like you look at current data and you throw it away and you only like reflect information in your current value function. And
more or less from like exactly from the memory perspective, like it has.
This is different from that.
Okay, interesting. Okay, thanks. Yeah.
You're welcome. Okay, this is a classical algorithm fiduciary derivation. Basically, just minimize the Bellman arrow.
I had a question here. So maybe I was late by a few minutes. What is T hat H here? Is it different from T H?
Is an empirical Bellman operator. Basically, the Bellman operator here assume you know the transition and you're taking expectation. Here and replace this expectation by empirical average.
Right. Right.
Okay. Good question.
Sure. Another quick question. Are you going to assume, I'm just asking about the assumptions in your results between different steps in an episode, are you going to assume that the sampling is independent, or do you have, it's basically
No, I'm not going to assume the sampling is between different episodes. It's not independent because my policy is going to adapt it according to the previous randomness.
No, but so, you take this expectation, or when you get the T hat H, When I look at t hat h and t hat
this is not
+1.
our algorithm. This is like a fitted curation, the textbook.
Oh, okay, all right, sorry.
Yeah,
sorry.
I'm not saying I'm using. I'm saying like I'm doing some principle similar to this. Yeah. Okay. So this is a text algorithm. I think you raise a very good question. So basically, this is a classical textbook algorithm about fitted curation, but clearly this algorithm kind of like assumes something about you already given the data, and so that you can take like doing average over data, and you have the empirical like Bellman operator. But it hasn't say anything about how to collect data, which is the next topic we say is a major difference between supervised learning and reinforcement learning. So in the supervised learning, we know this is like the scenario where samples are already given at the very beginning. So there's nothing you need to do about how to smartly collect data. I just use the data to analyze the supervised and put it into a supervised learning model and eventually output a classifier. However, this is not a reinforcement learning scenario, and we're looking at the online setting or exploration setting, where the agents and the environment are in a closed loop. So in each step, environment is going to feed like or each episode, environment is going to feed you the state and the reward, and the agent is going to take some action to like influence the environment. So whatever the sample you're going to collect it actually is affected by whatever the policy you use to collect those samples. So they're not independent, and you also need to specify how you're going to collect the samples. If you just play some garbage policy and the data you collect is also garbage, it will not tell you too much about what is a dynamic system info, like for some important parts. So this also, once we talk about collecting samples, that means we need to say what is a policy I'm going to use at every episode to collect my data. And this naturally relates to a very important question about exploration versus exploitation. That is, if I only play 10 episodes so far, I only have a very limited knowledge about my dynamics. So what I can do is I can play some greedy policies. That is the best policy based on the knowledge I have so far, but it may not be the best policy if I have all the knowledge. So a good way to learn the model should somehow balance both exploration versus exploitation. That is, I somehow need to exploit my current knowledge, and sometimes I should also just explore some place I have never been visited before. And so one of the very naive way to do the exploration is so-called epsilon greedy. That is, with major probability, I'm going to take a greedy action that greedy with respect to the existing knowledge. And with some small probability epsilon, I'm going to take some random actions. And this strategy is okay-ish for bandit problem, but in terms of reinforcement learning, because we have a sequential correlation, this becomes very bad. It turns out it's going to require something an exponential number of samples. That is exponential in terms of it depends on the length of the game. So for bandit, length is 1, so it's okay. But for any reasonable game, for example, you have a length 50, 100, and this number of samples are like huge. So clearly, we should not do this exploration strategy. And you probably know in the bandit scenario, in the bandit setting, there's a smarter way to do exploration that is so-called upper confidence bound. Essentially, upper confidence bound, go back to the bandit setting. Here, if we have 4 arms, I want to pull the arm that identified which arm is the best. So in this scenario, I would have a confidence set for each arm that after a lot of pulls, I say my true reward is going to land in this confidence set. And the upper confidence bound algorithm is basically I pull according to the highest upper bound. So in this case, the upper bound of the confidence set is for arm A is the highest. So I'm going to pull A next. So basically, high level principle is I want to be optimistic. I'm assuming the best in my confidence set, and I pick according to that. And this way, I can do efficient exploration. And it turns out this strategy can be extended to reinforcement learning. It's kind of like an old story for the tabular reinforcement learning. But what's new for function approximation is in function approximation, how we design this confidence set so that we can apply this upper confidence this principle. So our approach is actually very simple. So we again look at the fitted Q iteration. As we already said, fitted Q iteration is basically I'm looking at my value as a arc mean of the historical data, minimize the empirical Bellman error. where we denote it as this LD of FQH plus 1. So in order to build a confidence set, so we know this thing in the argmin is kind of give me a point estimator. However, in order to say something about a confidence set and to do upper confidence principle, we don't want just a point estimator. We do want to have a confidence setter. So we say with high probability, my optimal value is going to land in this set. So what I'm going to construct a confidence set is not just the minimum. I'm saying, okay, my confidence incorporate all the functions, all the value functions, so that the empirical Bellman arrow can be slightly larger than the minimum. So this is the minimum of the Bellman arrow. I'm saying I allow some beta tolerance. So as long as my value function gonna give me some Bellman arrow that is just slightly higher than the minimum value of the Bellman arrow, I'm still okay with that. And this beta is determined by the statistical arrow. So basically, we can compute how much tolerance we would have in this beta. And this is just our confidence set. And this confidence set is defined for QH. And in R, we just concatenate all the confidence set together, and which gives our confidence set for the value function. BJ, you have a question?
No, I think you clarified the thing. I was going to ask, this is, yeah, you don't have if H, and it's so I think you clarified it by taking the intersection, you get something which is
you get an intersection. So you get a value function, you get a confidence set for value function at every step, basically the entire value function. Okay.
And here we are not worried about, again, the computation complexity, because solving this over all the function class could be extremely hard, right?
Right. Yeah. So that's why I'm saying it's kind of like ERM. We assume like we have a minimizer, and here we assume we have the confidence set that is like defined by this thing. But yes, optimizing over this set is like a very computation intensive. That's why I'm saying like we're not dealing with computational efficiency.
And also, are you going to talk about how to pick the value beta here, or like any arbitrary
beta is somehow computed by theory. It turns out it's just some constant times logarithmic of the like log of the covering number of this function class f.
Okay.
It does not depend on some it does not depend on Bellman-Eluder dimension or some other complicated combination. It's purely just some uniform concentration. So it's only log of the covering number.
Thanks.
You're welcome. And so finally, this is just the algorithm, and our algorithm is quite simple. I will just explain it. So the first step is optimistic planning. So just recall we can imagine the fitted iteration is a special case where we pick beta equal to 0. So in that case, all the value function I'm going to pick is just the minimizer, and this is fitted iteration. So now what I'm doing of this B confidence set is just like a relaxation of the fitted iteration. And now I have a set of the function, a value function, instead of just a single value function. I'm going to do optimistic planning. That is, I'm going to look at the value at the very first step. I'm going to pick the value function within this confidence set so that I can maximize the value at the first step. And this is my value fk. I'm going to just take the greedy policy with respect to that value fk. And this is basically only non-trivial step, and the remaining part is quite straightforward. Basically, once we have this policy, we just use this policy to collect one trajectory of data S1A1 to SHAH. That is like 1 episode. And once we have 1 episode, and then we can put this new episode data into my data set. And now I need to update my empirical Bellman operator, so I can update my confidence sets. I have new confidence sets, and I'm going to repeat this process going on and on. Okay. So clearly, this is just an optimistic variant of FQI. We can, as I already said, when beta is equal to 0, this is just FQI. And now it's kind of like slack realization, and we do optimistic plan of FQI. And the key idea here is so-called global optimism and local confidence set. We call this confidence set a local confidence set because you don't look at the Bellman arrow at each step. But the global optimism, that is, we only maximize a single criterion, that is the value function at the very first step. So just recall this is very different from tabular setting, where in each step, I'm computing an upper bound of value function. In function approximation setting, if we're doing that, we need a lot stronger assumptions about the structure of the problem, and which turns out to be not true for a lot of practical problems. So by doing this global optimism, that is, we no longer require like intermediate value function, for example, value function at the second step, value function at the third step to be optimistic. I only require the value function at the very beginning to be optimistic. This way, I kind of I require much weaker assumptions, and algorithm is also much cleaner. This is why we call the algorithm called global optimism based on the local fitting, a Garf algorithm.
Hey, there's a question in the chat. I can read that to you. The Garf algorithms. Oh, okay.
Yeah,
you want me to read? Oh, you can see it. Okay, sure.
Yeah, the question is: the Garf algorithm looks very similar to follow the leader for online learning. Is there theoretical connections between these two? I would say this is also very close. I would say this is even closer to the like UUCB algorithm, like to the bandit, because this is stochastic setting, and it's not adversarial setting.
Yeah, that's what I about to say. It has a lot of similarity with that.
Yeah, there is a lot of similarity about this online setting. Yeah. Good. Okay. And okay, so this is all about the algorithm. So it's quite simple. It's just I've built some relaxation of confidence set and do optimism planning. And next question is, what is the class of reinforcement learning problem they can deal with? So okay, so the algorithm is like pretty simple. It doesn't actually depend on anything. Like I don't input any like a Bellman-Eluder dimension or anything like. But we need to identify a class of problem so that this problem is solvable. So the class of problem, so this algorithm is can solve those class of problem. So what we found is a class of problem so-called low Bellman-Eluder dimension. We already said it's kind of include like two generic classes we already have so far. So what is this low Bellman-Eluder dimension? I will just give like a vague intuitive like definition of it for this talk. So the Bellman rank is done by MSR group in 2017. It basically says I'm not looking at function class. I'm looking at so-called Bellman arrow, and the Bellman arrow for each Bellman arrow of function, because I have a function class, a value function class, and that will induce a Bellman arrow as a class. And the Bellman rank is essentially the linear dimension of this Bellman arrow class. And the later work, so-called lower Eluder dimension, they look at Eluder dimension, but they only look at the Eluder dimension of the function value function class. So the Bellman-Eluder dimension is basically says we believe for reinforcement learning, the value function class is not something intrinsic or we should look at. We should look at the Bellman arrow class, which is more intrinsic to the reinforcement learning problem, and then we look at some Eluder dimension of that. And this is just high-level intuition. But in terms of techniques, we need to define some modification of the Eluder dimension to distributed version. And I will leave the details to our paper. Basically, this is a high-level intuition. So we look at the Bellman arrow, and we look at Eluder dimension. Eluder dimension is like a superclass of linear dimension. It's like more general. So this is better than linear, and the Bellman arrow is like a better than value function. We're kind of like getting the both of the two. So that's why our class is larger. And finally, this is the theoretical guarantees we can say. Assume we have both realizability and completeness, then Garf algorithm is able to output an epsilon optimal policy with high probability in the following number of episodes. Episodes is like how many rounds you need to play the entire games. And the number of episodes is h squared d log nf over epsilon squared. Okay, I need to say slowly about what each term is. First, h is the length of each game. So it's h squared dependence. And d is what we have here is a Bellman-Eluder dimension, which in the linear function class, you can think it's just a linear dimension d. And for like kernel, it's kind of like effective dimension. It's just some intrinsic dimension measure of the complexity measure of the function class. And this nf is the epsilon covering number of the function class f in terms of the infinite norm. And we have the logarithmic dependence on this nf. And we already said it's also appear in the beta is a choice of the confidence set. And over epsilon squared, epsilon is like tolerance. Okay, and basically everything is polynomial. And most importantly, this only depends on the Bellman-Eluder dimension. For example, in the linear case, it only depends on the dimension of the linear function class. It does not depend on the number of states or actions. So which we kind of like say it's very important for like large state space or like general function approximation, have no dependence on the number of states. And furthermore, we can say D dependence, like this Bellman-Eluder dimension dependence in some subclass. For example, in the linear class, is actually, you can prove it's minimax optimal. So this is pretty sharp in terms of B dimension dependence. So the high level takeaway here is we do have a generic algorithm that is able to learn any problem in this generic function in this generic class sample efficiently, that is in polynomial number of samples.
Gee, I have a quick question. So this, as you said, the result relies on realizability, and you had a different algorithm to take care of completeness.
Right.
Is there given a function class and a problem, is there a way to computationally check that it's realizable, the problem lies in the class or not, or is there no way to do it?
I don't think it's kind of like also some like drawback of existing theory. I don't think realizability is checkable by just looking at data. Okay. Because realizability is assuming the optimal value function is in this class, and if you already have the value function, optimal value function, then you're down. I'm not aware of any way like we can check this assumption. It's just assumed.
Thank you.
Good. Okay. Since I don't have too much time to talk about multi-agents, so I will just be pretty fast about this part. So far we kind of like we developed a theory, like a very generic algorithm, and also like about the function class, like also really rich function class to deal with function approximation. In the multi-agent setting, we will consider like a more general model, so-called Markov game. You can build as a generalization of the MDP. So that is it's kind of like very similar to MDP, but instead in every step, I'm having both players taking actions. So first player will pick A1, and second player will pick B1. And in this case, the transition will depend on the current states and both players' actions. And the immediate reward will also depend on the current states and both players' actions. And what is optimal strategies in this case? There will be like a little bit different to define, because in MDP, basically I have a single player and just want to maximize the cumulative rewards. Here, we need to introduce a few additional important concepts. The first one is so-called best response. That is the strategy that best exploit opponent's strategy. For example, we can take a rock, paper, scissors as an example. The best response of rock is just always play paper, and so that I can always win. So I will have a strategy that exploits your strategy. And the Nash equilibrium is basically the optimal strategy if I'm assuming my opponent is always playing my best response. For example, in the rock, paper, scissors case, if I'm just playing pure strategy that a single action, my opponent can always counter it by play the other action that always gonna win over me. So what I'm gonna do is I'm gonna play a randomized action. I'm gonna randomized strategy. I'm gonna play a mixed strategy. I'm going to play rock, paper, scissors uniformly with 1/3 probability of each action. So in this case, no matter what my opponent plays, because we're gonna play simultaneously. So even though they know my strategy is like play uniformly, they have no way to counter it. Eventually, and this is like optimal strategy I'm gonna have. This is so-called Nash equilibrium. And in the Markov game setting, in the multi-agent 2-player zero-sum game setting, Markov game, we also have a concept of Nash equilibrium. That is an optimal strategy, assuming my opponent is always playing the best response. And this is target we're trying to find. Okay. So to find this Nash equilibrium, Nash policy, let's call it Nash policy, we can still use the so-called Bellman optimality equation. And the only difference is in the single agent setting, the Bellman optimality equation, we only have max over the action for the first player. And here, because it's multi-agent setting, so we instead of max, we have both max and min over the first player and the second player. And by von Neumann's minimax theorem, we know the order here it doesn't matter because it's like matrix. This is like a main matrix of A and B. So min max is equal to max min. sorry, I should not say a single policy here. This should be a mixed policy. So it's kind of like a max over simplex of A. It's kind of like a mixed strategy over. I can play a probability of action. And we still have a multi-agent version of field iteration that I just want to minimize the empirical Bellman error. And the only difference is like this Bellman operator is now defined by minimax instead of just max, and just max in single agent setting. And okay, and this is like our base algorithm again. But similar to a single agent setting, we still need to say how we're gonna collect the samples. It's kind of gonna say like what policy you're gonna pick. So there are several options. If we're gonna follow whatever we did for the single agent setting, one way is like we let the both agent play the optimistic Nash policy. That is optimal policy defined by this like minimizing the empirical Bellman error and based on existing knowledge. And turns out this strategy has some problem. So it may not explore some highly suboptimal subgames. So that means for some subgames, it might be highly suboptimal. So for example, if you play Nash strategy and your opponent play Nash strategy, you guys should never be there just because those are very bad for you or for your opponent, so they will never lead you there. But just because both players play optimal Nash policy, they may never gonna go there. So you haven't learned anything about that subgame. So you basically you have no idea about subgame. So in the case but by definition of Nash equilibrium, we're saying we want to be optimal against batch response. So if I'm against some opponent that is not playing Nash policy, but that is playing some policy exploit my current strategy, he might lead to those subgame, although it's highly suboptimal, but just because I have no idea how to play it, so I might still perform terribly in those subgames. So that's why we're gonna change to another approach. This is so-called exploiter approach. That is, we no longer treat it symmetrically. We have a main agent and an exploiter. So the first agent is called main agent. We're gonna play optimistic Nash policy. And the second agent, he's gonna help fix the problem of the first agent. So he's gonna play the optimistic version of the batch response to the current policy of the main agent.
Hey, just want to get some clarification about the game. Is this a symmetric game, like both agents?
This is not necessarily a symmetric game, but
okay. But here,
if you want to play the Nash, if you want to learn the Nash policy from both agents, you can do it twice. So you make the first player as a main agent and the second player as an exploiter. You learn the Nash policy of the first agent first.
So do you assume both agents, you can control both agents policy?
Yeah, we're dealing with a self-play scenario.
Okay.
It's kind of like
see then why it's a game. I'm a bit confused because you can control both agents.
During the training is you can play you can control both agents, but essentially okay. So essentially what your target is, you want to learn the Nash policy so that so it's kind of like eventually to learn a game, I want to learn a policy of a single agent so that no matter what my opponent is, I can still perform pretty good. But to learn it, I can coordinate with my opponent too. So it's kind of like during the training phase, they can cooperate.
Okay.
During the test phase, they have to play against any opponent.
I see. Okay, thanks.
So I had some questions also on the model. So it's a symmetric information game though, right? Both players get to see the state. On the
both
state
agent is going to see states. Yeah, there's no
symmetric information game. Okay, that's good. And when you say you're looking, so are you looking for Markov perfect equilibria, or are you just looking for a Bayes Nash equilibrium in Markov strategies?
What does it mean?
Well, I mean, are you looking for subgame perfect type thing where basically you have sequential rationality given any
by what I mean here, like Nash equilibrium is actually already subgame perfect, not Nash equilibrium.
Okay. So you're not just looking at a Bayes Nash equilibrium, and you're looking at like Markov perfect equilibrium. Okay.
Yes, and also I think the Markov game is kind of like a little bit special. I think basically it's similar to the matrix game. So whatever the Nash policy you find, you will always able to find a subgame perfect Nash equilibrium have the same value.
Yeah, and plus it's a zero-sum game in your case, so you'll get the value is the same no matter what. Each equilibrium has the same value. Right?
Yeah, yeah. And we do want a subgame perfect equilibrium. So that's why I'm saying like so we want subgame perfect so that we can play against the opponent that will play best response. So in the option one will fail exactly because it's not necessarily subgame perfect or close to subgame perfect.
Thank you.
Good point. Thanks. Okay, so I will just quickly go over the rest. Sorry, I'm running out of time. And the algorithm is basically very similar to the GARF. The only difference is like during the optimistic planning, the majorness play the optimistic Nash policy, and the exploiter will play the optimistic best response. And I will leave the detail about how to compute the best response. And the theoretical guarantee is also kind of similar. I still assume realizability and completeness. And then the Nash GARF exploiter will output some epsilon Nash policy within this similar number of episodes. The major difference is now this D is no longer just the B dimension, but Bellman-Eluder dimension, but the multi-agent Bellman-Eluder dimension. Everything else is the same. Okay, and this is saying this new algorithm is able to deal with multi-agent generic function. Essentially, we kind of like extend the principle of global optimism and this simple algorithm to the multi-agent scenario. And this multi-agent Bellman-Eluder dimension, the new complexity measure we defined, is able to deal with a lot of new problems that cannot be dealt with in the previous work. For example, prior work can only deal with tabular Markov games or linear function approximation of Markov games. However, our works can deal with kernel function approximation, rich observation, and the kernel feature selection, a lot of them. And basically, that's finish all my talks. In these talks, we developed our first line of sample efficient reinforcement algorithm. And so that I could address both challenges of multi-agency and general function approximation. So there are a couple of future directions I feel kind of very important extension to this line of work. The first one is our algorithm I feel is very generic, but our complexity measure I still feel might be a little bit limited. We kind of deal with this Bellman-Eluder dimension. But our algorithm actually does not rely on the Bellman dimension. We don't need to input Bellman-Eluder dimension. The algorithm can be independent of the number of that. So we are wondering whether we can identify some rich class of reinforcement problem that is beyond the low Bellman-Eluder dimension that can handle by this algorithm as well, or handled by some variants of this algorithm. And the second thing, as we said in the beginning, this is only about sample efficiency. We view this as a first step in dealing with general function approximation. The next step would be like how we deal with some computational efficiency algorithm, or if we don't have a computational efficiency, can we say some oracle efficient algorithm, for example, by assuming if we have some like a regression oracle and we just want to have some polynomial number of access to this regression oracle. And finally, those are all like theoretical algorithms. Eventually, if we want to make practical impact, we do want to test those in the real data set. So far, still a little bit far away from that, but eventually we do want to test it on the practical data set and see how the performance against the state-of-art heuristic algorithms. Okay, and this finished my talks. And thank you.
So I had a quick question on your uncertainty sets. I mean, the way you defined it was every function in the function class such that your Bellman error was within beta, right? Yeah, of the minimum.
Yeah. Sorry, this should be FH.
Yeah, no, FH. Yes, sure. I mean, yeah. But in some sense, that's where the computational issue comes. This is hard. But is there? I mean, and later on in your algorithm, you were sort of choosing the best, the one that met this beta in some under certain conditions, right?
The beta is fixed. Beta is
no, the beta is fixed, but in the beta BH, sorry.
I just want to maximize over this confidence set. Yes.
Yes, on that confidence set, and the computational issue comes in because that set may be complex, and then so you're trying to optimize something over a complex set.
Right.
Is there? I mean, if there's any structure on the problem, can you actually show that you can go for a subset of that and still be fine because the maximizer has some structure that you can exploit?
I would say the current. So if you're familiar with reinforcement, there exists some algorithm for tabular setting or for like linear function approximation that is basically value iteration with upper confidence bound. That is, instead of doing this global optimism, I'm kind of like are computing an upper bound for each steps.
Yes.
You can build it as a relaxation of this confidence set. I would say this confidence set is the tightest confidence set because it's like concatenation of them. And the VI UCB or like LSVI UCB is basically saying at every step, I'm having this confidence set and I kind of like compute an upper bound.
So you sort of expand it a bit in some ways.
Yeah, expand it in every step.
Yeah.
So that is a relaxation of this one.
But wouldn't that hurt your sample complexity or something? I mean, would if you do it in this
linear function I think in the linear function approximate in the tabular and in the tabular setting, I think that kind of relaxation does not come in terms of herd sample complexity, but it comes in to it requires some additional assumptions like a so-called optimistic closure, which is true for the linear MDP and for the tabular setting, but not true for the generic function approximation. For example, for LQR, it is not true. So we cannot use that relaxation essentially.
Thank you.
Basically, that's by doing that relaxation, by doing that relaxation,
you have to relax this to make it better, right? To compute it better, right? That's right. Okay. Yeah. Thank you.
You're welcome.
Hey, excellent talk. So let's see. Are there any other question, or if you have, then please feel free to unmute yourself. Otherwise, I have two general questions.
Sure.
Okay, maybe I can go ahead. So one question is about the multi-agent power. Like if we look at, for example, AlphaZero, right? During the training of AlphaZero, they are doing the self-play. But when they do the self-play, they assume the policy is the same policy, which means it's not like A and B, like a B is, how to say that, strategically chosen. It's still based on the policy like agent one is using. In that case, you can, again, assume A and B just come from some policy, right? What's the advantage of viewing like from game perspective compare with like, for example, looking at from the self-play perspective?
I feel, okay, I feel there are several ways you can talk about self-play. I think my terminology about self-play is basically I'm not playing against experts. So in my training, like I assume I can take control over the both players so that they kind of like, I need to control both of them to learn how the mechanism of the games and to exploit, eventually discover the Nash policy. But I think in what you just said, the self-play is more like both players are using the same policy, and they kind of like they just maintain one single policy because the game is symmetric in some sense.
It's not really the game is symmetric, right? In the AlphaGo, the idea is okay. I'm an agent. I'm gonna learn a policy. Eventually, I will play with someone else, right? And but I assume if I can, I'm a good player, and if I can beat myself, then I can beat all my opponents.
Yeah, it's kind of like
right.
That's kind of like what I mean by symmetric game, because for a lot of games, if it's symmetric, there's if it's asymmetric, there's no meaning about beat myself just because my opponent is playing different games. And I feel the symmetric game is basically a special case of asymmetric. I think even for Go, technically you should not say it's a symmetric game just because one player play first, the other player play second. So technically their game is kind of different. The strategy would also be different.
Yeah, so that's exactly my point. It seems like they're like kind of consider symmetry, like just incorporate that. It seems to work well in practice.
I think in theory, like whether consider the both players share the policy or just both players learn completely different policy, just view them as the asymmetric game. I think it's probably only cost a factor of 2. So I don't think it matters too much.
Yeah, so that's my question. What's the difference, right? From theory perspective. So you're saying maybe the factor of 2 difference.
I think it's just a factor of 2 difference.
Okay.
Well, I mean, some games need not, I mean, from what I hear your discussion, it seems like you're looking for a symmetric equilibrium in the case of AlphaZero. Even though
not necessary, right? You don't know who the opponent will be, right? So
no, but I guess you're trying to get a symmetric equilibrium. It feels like, I mean, if you're training in that purpose, And some games don't have symmetric equilibria. I mean, the equilibria are all asymmetric strategies, in which case I don't see why you would train to get to a symmetric equilibrium.
Well, I guess, I mean, for AlphaZero, the goal is to win as many games as you can, right? Whether it's the equilibrium point or not, or doesn't really matter. The goal is to try to make a policy which, when you compare with all kinds of the players, you can win with the highest probability.
Sure.
So it's not a fixed type of player. It could be any type of player.
So that's what I'm saying. Like in theory, what we can find is a minimax strategy. It's a Nash strategy. That is, I'm not necessarily gonna exploit. So for example, if I'm playing against terrible opponent, I'm not necessarily going to win him by a large margin. But what I'm guaranteed is that even I play against the strongest opponent, I'm gonna draw with them. So it's kind of like minimax sense. It's not like exploiting opponent very, very good, but it's a minimax.
Well, the thing with the zero-sum game is the following, right? I mean, basically the value is the same. I mean, so AlphaGo zero and stuff, these are all zero-sum games, right? I mean, so no matter, I mean, for all equilibria, the value is the same. Value of the game is fixed, right? So it doesn't. So in that sense, you're not going to change, go away from that value in the way, no matter what equilibrium you reach, and that's probably what they're using as an underlying factor.
Oh, in the Markov game, you can prove it's actually also special. It's kind of has a special structure as a matrix game. It only has a single Nash equilibrium value. So you might have a multiple Nash equilibrium, but they like connect. They're essentially
strategies might be different, but you'll have the same value. Once you have the same value, then it's it's a lot. I mean, it's still hard, but a lot easier than if you had different values for different equilibria. Then
I think the general sum multiplayer setting is very different. There you have a lot of non-trivial different Nash equilibrium, and it's much difficult to learn.
Thank you.
Okay, maybe I can quickly ask the second question. I think like in your work on Q-learning is whether Q-learning is efficient, you look at the regret, right? Sample complexity, regret perspective. And in this problem, you look at, my understanding from like optimality gap perspective. So eventually you want...
Actually, I simplified the talk, so I say the sample complexity, but in the paper, we also do the regret.
Oh, okay. Okay, yeah, so my question is this too, like, I think for the Q-learning case, we look at the regret, but we're not necessarily looking at if we at a certain time we stop the learning, what will be the performance of the policy? So here you said you have both. You also have the regret. Can you comment on what's the regret during the learning process?
I think I would like to say a little bit about the techniques. There are some technical details about this. Okay, so the immediate like for this because this kind of algorithm is like it's kind of like optimism style, so it's very similar to UCB. So in terms of proof, I think regret is the most natural thing to do, and regret is also stronger than sample complexity, because sample complexity essentially says in the very end I'm gonna output a reasonable policy. This is okay, and regret is kind of saying over the entire path I cannot do something cumulatively very, very bad. So regret is stronger. But in terms of techniques like how to change over them and like transfer from both of them, I think for sample complexity, you should typically will not directly transfer to regret. For example, this is 1 over epsilon square sample complexity. If we want to do the regret, like standard ways like exploit then explore then exploit, which will give you t to the 2 over 3 like regret, which is kind of bad. So this sample complexity 1 over epsilon square sample complexity would not directly go to square root t regret.
But so even for regret, my question is, if we are looking at regret or at a certain time,
how to transfer from the regret to the sample complexity?
No. Do you get an algorithm? Like, do you get a stationary type of algorithm at the end? Because
so there are a couple of ways to do it. So one way we can do is also is kind of like mentioned in those papers. We're a little bit loose in terms of we just do the online to batch conversion. So what we can say is once we have a square root t regret, we just output a random policy. Like
so you have to remember all the policy, then just
you have to remember, or you don't need to remember all the policy. You just first uniformly sample a number in the very beginning, and then you stop at that episode. And that policy you're going to guarantee to be perform epsilon optimal, like but only with constant probability. And to have high probability is slightly different. We haven't wrote it in the Q-learning paper, but later on we kind of figure out there are some stopping criteria. Basically, for the single agent setting, you kind of also need to have somehow construct auxiliary lower bounds. Those lower bounds would not be used in terms of exploration or picking data, but it would be used in terms of stopping criteria, like which iteration you're going to stop. And that iteration is going to guarantee with high probability to perform good. And in the multi-agent setting, since it will be easier because I already have that duality gap, so I'm consider both upper bound and lower bound. And I directly say that I consider the iteration where duality gap is the smallest, and I just output that iteration, and that is good enough.
Very interesting. Thanks. Yeah. Any other question for Chi?
I have a question.
Yeah, go ahead. Yeah.
So in multi-agent setting, do we assume that this is a zero-sum game or not?
Yeah, we assume this, and the work we talked today is like a two-player zero-sum game.
Okay, thank you.
Okay, it's almost 5:20, so I guess if there's no other question, we can end the seminar today.
Yeah,
Thanks, again.
See some of you tomorrow.
Yeah, talk to you tomorrow.
Thank you. Yeah, talk to you tomorrow.
Yeah, excellent talk. Thanks.
Thanks. Bye.
Bye.